Hey pre-calculus students, this is Module 1, Lesson 6. Today in this lesson we're going to cover a couple things. One is how to represent complex numbers as vectors. So in the last lesson we represented them as points in the plane. Today we're going to represent them as vectors, which we'll talk about that. And then we'll also be able to represent addition, subtraction, multiplication, with vectors in the complex plane. So we had done these algebraically before, but today we're going to be able to do them geometrically with our vectors. So let's jump right in with the do now. Mr. Wade is standing in the origin of the complex plane at the right. How would you give him directions to go to the point 4 plus 3i? So this is my little stick figure standing here. And I was just thinking in general, what would you tell him to do? And common responses we got, well, he would need to, this is our real axis over here, and our real part is 4. So he's going to need to walk over 4 steps, 1, 2, 3, 4 steps to the right. And then this is our imaginary axis up here. So 3i is up 3. It's right there. So he's going to have to also take 3 steps up. So maybe some common responses we got were maybe 4 steps right and 3 steps up. Nice. It says now draw a vector from where he started, and this is a typo, from where he started to where he ended up. This is called the resultant. So I'll sketch that vector in now. I'm going to draw this vector right there as an arrow. So what we want to establish in this lesson is that vectors, so this blue arrow that tells us we're starting here and overall we ended up there, can be thought of as a set of directions, basically saying we'll go 4 steps right, then go 4 steps up, and that blue vector tells you where you'd end up after you go that far. Cool. So let's practice with these vectors a little bit more. We can plot any number as a vector. We already plotted 4 plus 3i as a vector. Let's practice plotting some more. So in example 1, it says plot the number 3 plus 5i as a vector. All right. So down in my origin, all our complex numbers are just going to start at the origin, right there. 3, so real part of 1, 2, 3. Imaginary part of 5, 1, 2, 3, 4, 5. And I just sketched those notes in. I'm going to erase them afterwards to make our drawing a little prettier. But 5 is right there. So 3, 5 is right there. There's our vector. Goes from the origin to 3, 5. Great. Now the second part says find the length of the vector. So when we're talking about vectors, people mention they have a magnitude and a direction. So today we're going to start thinking about the magnitude, and we're going to do that right now. That's the length. So how much, how long is our vector? To do that, people noticed in class that this looks a lot like a triangle. We could draw a right triangle. And we know the side lengths of this right triangle. One side length is 5. The side length down here is 3. If we know the sides of a triangle, we can use our Pythagorean theorem, a right triangle rather, a squared plus b squared equals c squared, to solve for the missing side, or the length of this piece. I'm going to highlight it in green. We're looking for that length in green. Okay, well we know that a is 3 and b is 5, so we'll plug those in. 3 squared plus 5 squared equals c squared. But we also want to, so we can simplify that. That's going to be 9 plus 25 is equal to c squared. So 34 is equal to c squared. And if we take our square root, we get c is equal to square root of 34. So we used Pythagorean theorem here to get this. We're going to find in general there's a simple formula we can use for any complex number, but the length of the vector, I'm going to write our step here, was the square root of 3 squared plus 5 squared, which is equal to the square root of 34. Nice. So we plotted it. We also found the length of the vector. So now let's plot negative 3 minus 4i, negative 3 minus 4i, negative 3 there, minus 4i here. I'm going to label it negative 3 minus 4i. Notice it's just one arrow straight from the origin to the point we want to go to. Now we need to find the magnitude of this vector. So again, this time I'm actually not even going to draw the triangle. I'll draw it anyway. Over. So this length of this side of the triangle is 3. This side of the triangle is 4. So if we use the same format over here, we'd have the square root of 3 squared plus 4 squared. As I'm looking at this, I noticed, boy, it'd be nice if we could just take the real and imaginary parts of the complex number and plug them into those spaces in our little formula here. Let's see if it would matter. If I instead plugged in a -3 here and a -4 here, just copying them right from our number, not even having to draw a picture, that actually wouldn't change our number because 3 squared is 9 and -3 squared is also 9. So we had a good discussion about this in class. Basically, it's nice that we can just pull the numbers right out of our complex number and put them right in the formula. So that's going to be 9 plus 16, which is the square root of 25, which is just 5. So the length of that vector would be 5. So plotting vectors is really straightforward. It's really just drawing an arrow from the origin to the point, and then finding the magnitude. We have a formula now. Well, for any vector of this form, z equals a plus bi, we can use the formula. In every case, we use the square root, and then we plugged in 2 values, squared, and the 2 things we can just use are a and b. Those sort of correspond to the real and imaginary parts, or maybe the 2 sides of a right triangle, if we think of it that way. Let's look at the notation for this. These vertical things, they look like absolute value signs. Here they mean magnitude. But magnitude and absolute value are actually pretty much the same thing, right? If I ask for the magnitude of -2 or the absolute value, it's just telling you how much it is with the quantity. Well, it's just 2. In the same way, these vertical lines here tell us how long the arrow is, how much the arrow is. So magnitude, absolute value, they use the same symbol in math. Great. So that was sort of our first overview, plotting vectors, finding their magnitude. Next, we're going to dive into how to do addition, subtraction, and multiplication. So flip to the back side of your notes for this. This says arithmetic with vectors, so we're going to be doing our arithmetic that we had done algebraically in lesson 5, but now we're going to be doing it with vectors. So I gave us 2 vectors to think about here, z and w. And just like in our do now, I want us to think of these as sets of instructions. So a -3 and a -4i, if we think of it instructions, like me standing in the coordinate plane and this vector being directions for me to go somewhere, that would be like saying go left 3 and down 4. And then for w, that would be like saying go left 4, because that real part is -4, so that'd be left on our axis, and +7, so that would be up 7. So that's sort of our description of what these instructions, these vector instructions, are telling us to do. So first I'm going to draw these. I'm going to use red for z and blue for w. So z is -3 plus 4i. It just goes to that point right there. I'll draw a nice little arrow. Oop, my bad. -4i. -3, -4i is down here. So that's our vector z right there. Vector w is -4 plus 7i. Goes right up there. And I'm going to draw a vector right down to the origin like that. So we have our vector w. Sometimes I'm going to on default put a little arrow on top of our vector like that. In math, that means it's a vector. Usually in our text, in our binders, it'll be bold. So it'll be nice bold letters when it's talking about a vector. But it doesn't really matter too much in this class which notation we use. So I'll just leave them as the letters. Okay, so if we start to think about these vectors as sets of instructions, to do arithmetic in number 1, it asks us to find z plus w. So we can do this on paper really quick. We already practiced this in lesson 5. Z is negative 3 minus 4i. W is negative 4 plus 7i. Combining my like terms, negative 3 and negative 4 gives me a negative 7. Negative 4, positive 7i's give me positive 3i. So right away, we should be able to calculate that sum, and I'm going to plot that point on our plane here so that we can check ourselves geometrically. So we found z plus w, and now we want to confirm our answer geometrically. So thinking of these vectors as instructions, saying z plus w in vector terms would mean first go follow the instructions for z. So do what z tells you to do. That would be following along our red arrow and stopping right there. So I'm going to put a little guy right there. He's followed the instructions to do z from right here, and he's waiting. The next thing it says, plus do w. Now we have to follow w's instructions from where we are. So let's look back up. W said go left 4 and up 7. So if I'm starting here where the little guy is, I'm going to go left 4, 1, 2, 3, 4, and I'm going to go up 7, 1, 2, 3, 4, 5, 6, 7. So following our instructions, if I first go z and then I go w, I'm going to draw the w vector. Notice when I redrew it down here, it's just a translation. It's like we took this w vector and slid it down so that it started at the tip of z. If we go z, the red, and then we go where the arrow w tells us to go from there, it takes us right to our point, which is the sum. So in vector terms, this would be, we have to draw our resultant, which is what happened when we went z and then went w. So to do that, I'm going to start at my origin and draw a vector that goes from my origin to where we ended up, right? Like that. And that vector would be called z plus w. So let's kind of summarize what we did here. We thought of z and w as instructions telling us where to go from the origin. And if we start with z and say first go z, we started our origin, we walked down along our red arrow z, we ended up waiting right there where the little green guy is. And then we had another instruction that says and plus do what w tells you to do. Well, if we followed w's instructions, we went left 4 up 7, and we followed that blue arrow from our little guy, and we ended up at the final stage over here at negative 7 plus 3i. So to do these computations geometrically with our vectors, we just need to add up the instructions from where we start at the origin to where we end up. All right, let's check one more time with w plus z. If we instead went in the other direction, if we first went w, then went z, we expect this should get us to the same point, right? But let's just confirm that geometrically. So if I go w first, that means I'm starting here at the origin. I'm going to walk along my arrow to w, and I'll have my little guy waiting up here for further instructions. And then the next thing says, do what z tells you to do. Well, z says, it's kind of this downward slanty. It says go over 3 to the left and down 4. So over 3 to the left, down 4, or to kind of follow this arrow. That's z. It just translated, just moved it up to the other side. Go w, then z. That takes us right back to the same point, which is z plus w, negative 7 plus 3i. So that covers how to add them geometrically. We follow instructions, one and then the other. Now we need to talk about subtracting them. So here it says find z minus w. Let's do this on paper first, or in algebraically first. Here we just have a minus sign. Remember, when we have that minus sign, we need to make sure to apply it to both parts. So I like to rewrite it in a separate line, negative 3 minus 4i plus 4 minus 7i gives us 1 minus 11i. So that's what we expect algebraically to be our difference, z minus w. I'm going to plot that right up here, z minus w, 1 minus 11i. Okay. Now if we want to think about this geometrically, first it's saying, well, go to z, so follow z's instructions, so walk along our arrow z, stand and wait at its end, so I'm going to put another guy there. He's waiting at the end of z. And then go negative w, so go in the opposite direction that w would normally tell you to do. Well, normally, w tells us to go left 4 and up 7. If we wanted to go the opposite direction, we would have to go to the right 4, 3, 4, and down 7, 2, 3, 4, 5, 6, 7. So the right 4, and down 7. This would be like negative w. Starting at the origin, it goes down to the right instead of up to the left. So let's follow the instructions for negative w, now that we know what it is, the opposite of w, starting from our little guy right over here. So our guy's waiting there. He needs to go negative w, so he needs to go down, or to the right 4, 1, 2, 3, 4, and then down 7, 2, 3, 4, 5, 6, 7. And sure enough, negative w takes us right to where we expected to go, to the difference. Now we have to remember when I'm drawing these, we end up making a lot of little stray marks, so it's nice that I can erase them on the tablet. It might be nice to do this in pencil so we can erase our little scratches every now and then. And then I'm going to draw the overall vector from where we started before we started going at the origin to where we ended up after we went z and then negative w. So this big green vector would be z minus w, because that's the overall where we started and then where we ended up. All right. I'm going to take a second and clean up some of these stray marks on our drawing here. Again, after we use them, we don't really need them. They're kind of nice to show work as we go, though. Oops, keep w on there. All right. Then the last one says find negative w plus 2 times z. So this is basically saying go in the opposite direction of w, so go negative w, and then go 2 z's, so go z twice. Let's do this algebraically first. Negative w is negative 4 plus 7, so negative 4 plus 7i plus 2 times z, and z is negative 3 minus 4i. Algebraically, this is 4 minus 7i plus, distribute our 2, negative 6 minus 8i. And so this gives us negative 2 for the real part, and negative 8 minus 7 sounds like negative 15i to me. So negative 2 minus 15i. So that's a pretty big number. I don't even know if it'll fit on our graph, but let's see if it would make sense graphically. So fine, go negative w. Well, we already have a negative w drawn up here, so let's do that first. Go negative w, go down here, have a little guy. And then it says go 2z. Well, geometrically, that basically just means do what z tells you to do twice. So z tells me to go left 3 and down 4, left 3 and down 4. All right, so that takes me right there so far. That's 1z. And then I need to go another z, left 3 and down. I'm going to erase some of our work so we can kind of make a point. Left 3 and down, 1, 2, 3, 4. Maybe it would be like right there. Z again. Let's see if that makes sense. Does that point look like it could be negative 2? Yeah, it looks like it could be negative 2 and negative 15, 11, 12, 13, 14, 15. Looks like it would be exactly negative 2, negative 15. So when we have a double or a complex or a scalar like that, it basically just means do whatever instructions your vector told you to do, but do it twice. Okay. If I want to draw this resultant, we can't quite fit it all, but I can draw the first bit of it. It's going to go from the origin all the way down to, it's kind of going that way. I'm just going to leave it cut off right there. I'll really erase our string marks. Oops. So this walkthrough kind of showed us how we can think of our sums and our differences algebraically. We've already seen that, but also how we can start to think of them as vectors following a set of instructions, a set of directions from our origin. So to practice this a little bit, go ahead and flip to your binders in page S19 right here. For the vectors u and w picture below, draw the specified sum or difference on the coordinate axis provided. Now here we don't have any markings on the axis, so we don't actually know what u is equal to and v is equal to like we did before. So it's going to rely on us really just knowing how to do this geometrically. So let's first do this first one together. A is u plus v. So that's saying do u. So I'm going to follow along u, right here to the end. And then it says do v. Well, v says kind of go left and then up a little bit. So left more than 1 unit and up maybe like half a unit. So left more than 1 unit and maybe up like half a unit. So that to me looks like it would be like a v right there. V. So if we drew that v to help us along, so it says go u, then go v, now walk the end, and that's where we end up. So I'm just going to draw a resultant in green, and then erase some of our strokes along the way. And it's okay to leave some marks when you're making these drawings. Maybe just leave a little dashed and a v like that to kind of show where you got it. Then make sure to label your resultant u plus v. So I'm going to stop this part of the video. Go to your binder, try out these next 3 on your own. Remember looking back to our reference from up here about what it means when we get negative numbers, what it means when we get scalars. And then the next video, we'll wrap up and discuss these last few. And then you can come in and take your exit ticket.